Hey, there you are. Addition's pretty easy, right? I mean, it's the first thing you learn in math, and we don't even have to be taught how to do it. I can show you an image of an onion, and your wonderful meat computer can conjure up the image of a second onion sitting right next to it. Imagine two onions. Heck, imagine three onions. Not too bad. Okay. Imagine six onions. Imagining. Now think of 21 onions. It's getting kind of hard to think of all these onions. Okay, now dump 1001 onions onto that growing pile and keep adding an onion at 1 second intervals. What? We throw our hands up in despair. I don't know how I can possibly think of all these onions. I mean, obviously, the onions will keep growing infinitely, and someday the unholy mass of root vegetables will overpower the earth, the sun, the solar system, the entire observable universe. Surely there's no way for us to talk about how these onions will behave as time goes to infinity, right? We can't visualize what an infinite number of anything looks like, let alone onions. But we can talk about how an infinitely large sum of things behaves and acts as that sum approaches an infinite number of things. But let's come back down from infinity for a minute and talk about something more tangible. 1 plus 1 equals 2. 1 plus 1 plus 1 equals 3. 1 plus 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 1 equals 9. This isn't very nice to look at. Our shorthand to clean this up is 1 times 9 equals 9. Adding together one thing 9 times gives you 9 things. Multiplication is a convenient way of writing sums for static mathematical objects. Let's try it out with this pattern. 1 plus 1 half plus 1 third plus 1 fourth equals 25 twelfths. It seems kind of hard to write this in the same way as we did for 9 times 1. You can't really condense that down into just two numbers times each other equals a new number. We're probably going to have to do something different with this. We can tell that each term in the pattern is of the form 1 over n, where n increases by 1 in each subsequent term. Just like multiplication is a shorthand way of writing 9 ones added together, sigma notation provides a way for us to more neatly write 1 over n. To introduce this thing though, let's start off with the case of 9 ones added together. This is sigma notation. The bottom of the sigma symbol tells us what n value to start counting from. In this case, we start counting from 1 because n equals 1. The top of the symbol says what n value that we should stop counting at. The 1 inside of the sigma is the term that we will be adding to the sum for each step of the evaluation. In this case, just 1. Okay, let's evaluate 9 ones written in sigma notation. N equals 1, our sum so far is just the inside term 1. N equals 2, our inside term is still just 1, so we add that onto the previous term. Our sum is 2. N equals 3, our sum is 3. N equals 4, 5, blah blah blah. N equals 9. The final result of our sum is 9. Let's try this out with the 1 over n pattern. We had 4 terms, so our sum will cover the terms from n equals 1 to n equals 4. For n equals 1, our sum so far is 1 because 1 over n equals 1 when n is 1. For n equals 2, the term on the inside becomes 1 half, and we add that to the previous term. For n equals 3, the term becomes 1 third, do the same for n equals 4 to get 1/4, so the final result becomes 25/12. These two examples are called partial sums because they encompass just a partial slice of the terms of a sequence that you could keep adding on to forever. Say we change the number on the top of the sigma from a 4 to infinity. We now have the complete sequence of 1 over n terms up to n equals infinity. The sum of this complete sequence is called an infinite sum. Adding together all of these terms would be quite the task. Dare I say a super task? Anyways, doing infinitely many discrete steps of anything, including addition, just isn't something that can be physically accomplished. Instead of trying to find what exactly this sums to, it'd be easier to look at how the sum behaves as n grows. Here is a whole onion. Here's half an onion, a third of an onion, a quarter of an onion, a fifth. If I keep going and stacking thinner and thinner slices, how tall will the tower of onion be? Assuming these onions are non-physical abstract objects that I could cut arbitrarily thin, I could stack them, well, endlessly. The onion tower wouldn't have a defined height, it would keep growing forever. The infinite sum of 1 over n is called the harmonic series. Let's graph part of it. You can see that each term in the harmonic series keeps decreasing as the size of n grows, but it doesn't reach 0. If we step back and look at the series again, we can split up and group its items in different ways. The 1 over 3 can be rewritten as 1 over 4 plus some extra remainder, and so too the 1 over 5, 1 over 6, and 1 over 7 can each be rewritten as 1 over 8 plus some remainder. Each of the sections in parentheses is equal to 1/2. The sum can now be written as 1 plus 1/2 plus 1/2 plus 1/2, and since the series is infinite, there is always a way to regroup ever larger strings of terms together into something that equals 1/2. The sum is equivalent to an infinite string of 1/2s, therefore. The sum equals infinity. Sums that equal infinity are called divergent because they do not settle on a finite value. They do not converge. Now, it might be easy to look at the infinite sum of 1 over n squared and say that it also is divergent, because you could do the same grouping of terms. But remember that not all diminishing returns are created equal. Why? If the terms of an infinite series decrease towards 0 quickly enough, the trick of regrouping terms into chunks of 1/2 will soon require an infinite number of terms to regroup into a 1/2. Infinite sums that come to a finite total are called convergent. Exactly why 1 over n squared is a convergent series while 1 over n is divergent isn't intuitive. To see why 1 over n squared is convergent, we'll utilize something stronger than intuition, which math excels at: logic. 1 over n squared is less than 1 over n squared minus 1 because its denominator is larger by 1. Here, they are graphed together, and you can see that the curve of 1 over n squared is always below the other, even when zoomed in. If we can show that the series of 1 over n squared minus 1 converges, we will know that 1 over n squared converges, since each term of 1 over n squared is going to be smaller than the corresponding term for 1 over n squared minus 1. Showing that a series converges without calculus can be tricky, but luckily we can use a neat trick on 1 over n squared minus 1 to see what it converges to, if at all. The denominator can be factored, split apart, to look like n minus 1 times n plus 1. Now, if we could find something that adds together to make the 1 on the top of the fraction, we could split apart those two factors on the bottom of the fraction, and that would make the whole thing a lot easier to work with. This process is called partial fraction decomposition, but that's not super important for what we're doing here. I just want to show you that it works because questions need answers, and I don't want to leave you with questions. To find out what the top of the two new fractions should be, we'll set the original fraction equal to an unknown divided by the first factor and another unknown divided by the second factor. To find the unknowns, a and b, get rid of their denominators by multiplying. Now the expression becomes 1 equals a times n plus 1 plus b times n minus 1. Group the n terms and the non-n terms. Notice that the left-hand side doesn't have any n's in it, so the an plus bn must be equal to 0, and the a minus b part must therefore equal 1. You could do some linear algebra to solve for a and b pretty easily, or do it the old-fashioned way, but let's just leave that as an exercise for the viewer. What you should end up with is 1 over n squared minus 1 equaling 1 over 2 times n minus 1 minus 1 over 2 times n plus 1. Since these two fractions are equivalent to the first one, whose series we wanted to see the convergence of, we can look at what their series converge to. We'll have to start our sum at the n equals 2 term, because the n equals 1 term is an irrational number, which is okay for our infinite sum because the difference between n equals 2 and infinity is still infinity. Let's write it out. The denominator of the part being subtracted in each set of parentheses is exactly 4 less than the part being added. What's wacky about this is that after 1/4, the series contains every even denominated fraction and the negative of every even denominated fraction. The only two terms left over which don't have a corresponding negative somewhere in the series are 1/2 and 1/4. 1/2 plus 1/4 equals 3/4. We've just found what our infinite series converges to at n equals infinity. It's cool that we've found what it converges to, but it's even cooler that we've found it converges at all. We've been talking a lot about 1 over n squared minus 1, but remember 1 over n squared? Don't tell me you forgot. I mean, you two made plans. I mean, it came to your door and knocked, and you pretended like you weren't home and you left it out in the rain? Alone? Wow, Anyways, that's fine. The infinite series of 1 over n squared forgives you, because it knows where it's heading in life. A little hiccup like this won't interrupt its stride because it knows its fate is predestined, no matter what you do to it. That's right, the infinite series of 1 over n squared is convergent. Wait, why again? Remember how 1 over n squared is always less than 1 over n squared minus 1? Well, since we showed that the infinite sum of 1 over n squared minus 1 converges to a rational number, that is, to say that it doesn't blow up to infinity, the series of 1 over n squared also won't blow up to infinity because it's always smaller than 1 over n squared minus 1. So, what is sigma notation? It can be whatever you want it to be. No, seriously, you can represent any analytic function with a series. Okay, so maybe sigma notation can't be everything you want it to be, but it sure can do a lot for you. And its uses are most applicable to actual functions which you'd see out in the wild. For example, this is exactly equal to the function of sine x, but that's a topic for later. That's enough for one day. If you still don't feel comfortable with signal notation, feel free to rewind the video and watch any parts that you get stuck on. Now, if you'll excuse me, I've got a lot of onions to cook up. Oh, and hey, thanks for asking.